So we're going to continue, like I said before, to look at volumes of revolution. We're going to look at some different methods. The next one we're going to look at is a washer method. We're going to use this when we have holes cut out of our solid, of our three-dimensional figure. So see, for example, we're still going to be kind of looking at, what if we have a rectangle? Well, what if I have some space beneath my rectangle and then choose to not rotate it along the line that it butts up against, but instead rotate it along a line past that gap? So kind of something like this. I found this diagram on these two diagrams here on the internet and cut and pasted them on. So what happens when, again, I have that space? Well, when I revolve it around my axis of revolution, look at what happens. I end up with that little hole in the inside. Well, what if I were asked to find the volume of this washer here, is what we call it. It looks like a washer. So I've noticed that it is this big cylinder here, really. It's this fat cylinder with this little cylinder taken out of the middle of it. Well, the volume of this whole thing without the hole, the volume of the whole cylinder, we looked at in the last video, is going to be pi times radius squared. In this case, my radius is labeled as big R, times the height of the cylinder, which is labeled as W. I suppose I don't need to keep it on there. So then I'm going to have to take away the volume of the inside cylinder. Well, the inside cylinder has a radius that's labeled of R. So I'm going to do pi times R squared, because remember I'm finding the area of the base times the height of the solid. The height of that inside cylinder is still W. And if I factored this, I'd get pi W times the big radius squared minus the little radius squared. And that would give me the volume of my solid of revolution that we call a washer. So what if I had, instead of just the one washer, what if I had a whole bunch of washers? How can I find the volume of that whole thing? Well, I'm going to sum up, starting at x equals 1, up to some amount of washers, depending on how many washers I cut it into, just like before, depending on how many rectangles I cut it into, of pi W times big R squared minus little r squared. And I'm going to get as many washers as I can. In fact, I want to take the limit as my number of washers approaches infinity. And now what is r squared representative of? Well, isn't it my function? Because isn't it the distance from the middle up to the top of my curve? So I'm going to go ahead and replace this with my function and replace this with my other function. Then I can say that the limit as n approaches infinity of x equals 1 up to n of pi w times my f of x to the I being my upper function minus my little f of x to the I being my, oops, I forgot my square, being my lower function, or my large radius and my small radius. How can I change that into an integral? Like this. I'm going to pull my pi out since it's a constant. I'm going to go from some a value up to some b value in terms of x. R of x squared minus r of x squared, where r of x is my big radius or my top function. Little r is my small radius or my bottom function. And then dx is going to be what stands for my height or my width, depending on how you're thinking of it, of my cylinder. So let's go ahead and use this formula to solve for some volumes of solids of revolution. In the first example, I want to find the volume by revolving the region bounded by the graphs y equals square root of x and y equals x squared about the axis. So I tried to find a picture of this on the internet because, as you know, the drawing of solids for me is not very good. So it's close. Notice that this is y equals x, not square root of x. So I'll draw it, and I'm going to end up with the square root of x, which remember is kind of that arm function, and the parabola x squared. So I want to take that. I'm going to use this as my region. I want to rotate that region in yellow around my x-axis. And when I do, it's going to kind of look, so like I said, not quite the right function, but very similar. I don't know, what would you call this? Like a pyramid, a horn, a cone? I guess a cone. It's going to be kind of this cone shape, but it's going to have this inside cut out. So because I have some of it cut out, since I'm missing part of it, I want to use my washer method. So the way I'm going to do that is, first thing I'm going to do is I'm going to go ahead and set my two functions equal to each other and figure out what my limits are going to be. So when does the square root of x equal x squared? I'll square both sides and say when does x equal x to the fourth? So 0 equals x to the fourth minus x. 0 equals x times x cubed minus 1. So either x equals 0 or x equals 1. So I'll have an integral going from 0 to 1. And I'm going to go ahead and I'm going to say, all right, so now I have to figure out what's my big radius, what's my small radius. Well, if I draw myself a rectangle here and a small rectangle, notice that my big radius is going to come from this rectangle, my small radius from this. So my big radius is the square root of x. So according to my formula, I'm going to square root of x squared minus my little radius, which is x squared squared, dx. I can go ahead and put this into the calculator, and when I do, I get about 0.942. Looking at the next two examples, there are 3 examples total. I want to find the volume of the region bounded by x squared plus y squared equals 25, and the line y equals 3. I want to rotate around the x-axis. Let's see. Since I'm rotating around the x-axis, I probably want my functions in terms of f of x. Therefore, in terms of y. I like that it's in this form because I am familiar with x squared plus y squared equals 25. I know that that's a circle with a center of 0, 0 and a radius of 5. So I'm going to go ahead and sketch that, and I have the line y equals 3. So here's my line y equals 3, 4, 5, 0, 0 with a radius. And then my circle that I'm going to have is going to look something like that. It's going to be this big circle that comes all the way, well, the center is 0, 0, so I guess I'm kind of more oval. Probably be stretched out a little bit more. However, it's going to look something like that. So I'm taking this area in between these two curves, and I want to rotate it around the x-axis. Well, if I rotate this around the x-axis, this is going to give me this whole area right here as a big gap. It's almost going to look kind of something like, I guess, it's going to be like this big kind of washer, I guess. Kind of something like that. So what am I going to do? Well, I'm going to have to figure out, first of all, I'm going to have to figure out where do these two graphs intersect. And I'm also going to have to figure out what is my big radius and what is my small radius, sorry. So the first thing I'm going to do before I figure out where they intersect, I think I'm going to go ahead and, so I know that I'm going to be doing a to b f of x. So I guess I can do r of x squared minus r of x squared dx. So I want everything to be in terms of f of x. So I'm going to solve this for y. So I'll end up with y equals 25 minus x squared, the square root. And I'm not going to worry about putting plus or minus because it's going to, when I put it in here, it's going to square it anyway. So then I'm going to go ahead, and I can see that I only want the stuff above the axis anyway. I'm going to go ahead and figure out where do these intersect. I'm going to say when does 3 equal the square root of 25 minus x squared? I can square both sides, and I can say when does 9 equal 25 minus x squared? Well, I know x squared is 16, so I know x is plus or minus 4. So this must be negative 4 here, this must be positive 4 here. So I'm going to have my integral from negative 4 up to 4. So if I look at my rectangles, my big R is going to be this here, which is under the curve y equals the square root of 25 minus x squared, minus my little radius is going to be under that line there, which is y equals 3 dx. And then I'm going to go ahead and put that into my calculator, and when I do, my calculator gives me approximately 268.083 for the volume of that solid that is created. Looking at the final example, just like we've seen before, I don't always have to do I do not always have to do vertical rectangles. I do not always have to rotate around a horizontal axis like this one or this one, for example. But what happens if I have a vertical axis? So notice my formulas are the same. So here's the formula from the last time where we learned what if there isn't a hole? What if I don't have to use my washer method? And what if I do have a washer method? Then it's going to be big Y squared minus small y squared, or big radius squared minus small radius squared. So I want to find the volume of the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. So if I look at what that looks like, I have x squared plus 1. I have y equals 0, so y equals 0 is right here. X equals 0 is right here. X equals 1 is going to be right here. X squared plus 1 would be a parabola. I'll just draw this half of it since I have this restriction here anyway. So if I kind of come up here, it's kind of a terrible drawing. Make it a little bit more accurate. There we go. And so, okay, so now I want to rotate it around the y-axis. So I'm trying to take this and rotate this here. So notice that it's in between y equals 0, x equals 0, and x equals 1 in my curve. I'm taking this here, and I'm going to rotate it around the y-axis. Well, notice that down here, I don't want to use the washer method. I don't have to, I'm not going to get a hole at all. But up here, I am going to get a hole. So I need to figure out where does this function here, this x squared plus 1, intersect with this function here, this x equals 0. Well, when x equals 0, oh, let me change colors. That's not a very good one. When x equals 0, notice that y equals 1. So if I'm looking at an integral from 0 to 1, I'm going to use the previous method I learned. So I'm going to do pi times, all I'm going to do is say, I'm going to take technically my right curve minus my left curve. But notice my left curve is just 0. So I'm going to take this right curve of x squared plus 1. Oh, I'm sorry, this isn't x squared plus 1. This is 1. So my curve of 1 dy plus, I'm going to add to it using my new technique from 1 up to. I have to figure out what I want to go up to. In order to do that, I'm first going to say, okay, so if y equals x squared plus 1, I never got this in terms of f of y. So I'm going to solve for x, so I'm going to subtract 1. So therefore, f of y, or x, so x equals f of y equals the square root of y minus 1. So in order to figure out on this next piece, I know I'm starting at 1. How high am I going? I'm going to say, when does the square root of y minus 1 equal my other curve 1? So I'll square both sides, and I get y equal minus 1 equals 1. I add 1, I get y equals 2. So I'll go from 1 to 2. And I'm going to go ahead and rotate that around. So then my big radius, I'm going to here. My big radius is going to be my outside function of 1. My inside radius is going to be this little rectangle, which is represented by, oops, where's my function? By my f of y here, the square root of y minus 1 squared dy. And so now from here, what I can do, and I forgot my pi out front, I always forget that. From here, what I can do is I can go ahead and integrate each piece. Doing that, in the front, I end up with about, I left it exact. I get about pi, which is about 3.14, plus I wrote pi over 2. So I get 3 pi over 2, which is approximately, let's see, 3.14. Pi over 2 is about 1.57. About 4.71. So depending on how you write it. So that is going to be the washer method. So again, if it's butted up against something and there isn't going to be a gap, we use the disc method that we've previously learned and practiced. If there's going to be a gap at all, that's when we use that washer method. So, but otherwise everything's the same. Make sure if you're rotating around a vertical axis that you're making sure that everything is in terms of y. Your function is in terms of y as well as your limits. If instead you're going around a horizontal axis, make sure that your function is in terms of x, including the function and the limit.